in this lesson, we will understand the idea of angular momentum of a rigid body. Now, we know that for a single particle, angular momentum L is defined as the cross product of its position vector r and its linear momentum p. That is to say, we do know how to calculate the angular momentum of a single particle. So, if we extend this idea to a rigid body, that is basically a system of particles or a collection of particles, the total angular momentum of L for this system is nothing but the vector sum of the angular momentums of all the particles. And the right hand side can be written in short form as sigma small li as I changes from 1 to n. Now, the angular momentum of each particle can change with time, maybe due to the interaction between themselves or due to the outside forces that act on them. And when this happens, we can find the change in angular momentum L of the system by taking the time derivative of L on the left hand side, and this should equal the rate of change of momentum of each particle in the system, that is the right hand side. But then we also know that dLi upon dt is by definition the net torque on the ith particle, and therefore this equation can be rewritten as dl upon dt is equal to sigma t net I as I changes from 1 to n. That is, the rate of change of the system's angular momentum is equal to the vector sum of the net torque acting on each particle. And these torques can include internal torques that often result from forces between the particles, and external torques that may be a result of forces on the particle from particles or objects external to the system. But we must remember that internal forces between particles occur in equal and opposite pairs, that is governed by Newton's third law, and these tend to cancel each other out, and as a consequence the torques add up to 0. Therefore, the torques that can alter the total angular momentum of the system would be external torques only that act on the system. So, if torque net represents the net external torque on the system, we can write this equation as torque net is equal to dl upon dt for a system of particles. And more formally, we can state this equation as the net external torque acting on a system of particles is equal to the rate of change of the system's total angular momentum L with respect to time. And notice that this equation is quite similar to the equation F net is equal to dp upon dt that is used in linear form. However, you must note that all the torques and the system's angular momentum should be considered relative to the same origin only. Again, drawing parallel from the idea that linear momentum is a product of mass and the velocity of the center of mass, we can say that for a rigid body, L is equal to I omega, where the rigid body is rotating about a fixed axis and I is the rotational inertia of the body about that fixed axis, and omega is the angular velocity of the body about the same axis. So, if you get a little confused with formulas that we use for rotating bodies, it's helpful to draw parallels with linear motion counterparts. So, here's a comparison of key equations in translational and rotational motion that you can also copy from the description below. And for a deeper dive into topics like rotation, angular variables, and rolling without slipping, I would suggest you head over to this playlist. And if you like this lesson, do give a thumbs up, and I'll see you in the next lesson.